Welcome to Lesson 8E, Reflecting Expansion Fan Analysis. This will be the last lesson in Module 8. In the previous lesson, we looked at the right side of the shock tube and discussed what happens when the shock hits the end of the shock tube for both an open end and a closed end. In this lesson, we'll do the same thing on the left side, where the expansion fan reaches the end of the shock tube. Again, we'll consider both closed-ended and open-ended cases. Here's a quick review. The left side has a higher pressure than the right side, and when the diaphragm breaks at t equals 0, we get a contact surface that moves to the right at speed VCS. On the right side, this produces a shock, which we've discussed in detail. And on the left side, it produces an expansion fan, which is a series of sound waves, with the leading wave moving faster than the trailing wave. This is what the process looks like on an XT diagram. The contact surface moving this way and the expansion fan moving this way. And at some time T1, which is here on the XT diagram, we plotted the XP diagram, noting that P3 must equal P2 since there can't be a pressure change across the contact surface, but pressure suddenly drops as the shock moves from left to right. Note also that V4 is 0, there's no flow there, and V1 is also 0. Now I'll introduce an XV diagram, also at time T1. V is V4 or 0 up to the expansion fan, and then it grows to some value V3, which is constant and equal to VCS, and also equal to V2. Then it drops suddenly to 0 again in region 1, where V1 is 0. This gradual change of speed from 0 to some magnitude V3 will become important when we look at the open-ended case. Let's consider first the closed-ended shock tube. I've zoomed in here on the left side of this process. At time t equal T1, we have our expansion fan as before on the XT diagram. The question is, what happens to this expansion fan as it hits this solid wall? Well, the leading wave, which is moving at A4, simply reflects like that, but the problem is it starts encountering all these other expansion waves, and it gets a little complicated. This wave will curve, and when this one hits, it'll curve in that way. The whole process gets a little complicated, as I said, but in the end, we end up with straight lines indicating a reflected expansion fan. I'll call this region here 6. What do we know? Well, just as this trailing wave had a speed of A3 minus VCS, this leading wave, when it finally settles down here, must move at wave speed A3 plus VCS, since this is still region 3. With gas speed VCS and speed of sound A3. What about up here in region 6? Well, we know that V6 equals 0 because of this solid wall. We did a similar analysis with the shock hitting the wall. But this region is complicated. Most people analyze this using the method of characteristics, which I don't have time to get into in this course. This trailing wave thus moves at speed A6, since this gas is stationary, much like it moved at A4 in this stationary region. But what about the pressure in region 6? Well, again, you'd have to do some analysis using the method of characteristics or use computational fluid dynamics to figure this out. It turns out that P6 is less than P4, and P6 is also less than P3, since this reflected expansion fan is now moving to the right, which means the pressure drops from 3 to 6, just as it dropped previously from 4 to 3. Now let me ask the students, does anyone remember a trick that I used when we studied potential flow to simulate a wall?
I recall that we used the method of images and superposition.
Right, Boris, and we can do a similar thing here. So here's an alternate analysis. We'll use the method of images and superposition, just like we did with potential flow. Namely, this is the real pipe with the expansion fan approaching the wall, and we add an imaginary part with an equal but opposite expansion fan moving the opposite direction. When these waves hit each other, because of symmetry, we can think of this as a wall. Let's look at several different times. At time t1, the contact surface is moving at speed VCS to the right, which is also speed V3 in region 3, but region 4 to the left of the expansion fan has 0 speed and pressure P4, which is greater than pressure P3. In the imaginary left side, this is also region 4 and region 3, and it's a mirror image of the real case. Now consider a later time T2. The expansion fan has moved to the wall, and the mirror image has also moved to the wall. There is no more region 4. Well, these waves start to cancel each other out, and since pressure P3 was smaller than pressure P4, these expansion fans lower the pressure at the wall. But in our analysis with superposition, there really is no wall, so these waves pass through each other, lowering the pressure. The contact surface has also moved to the right. At some later time T3, the contact surface has moved even farther to the right, and these expansion fans have passed through each other, so we now have a reflected expansion fan. Again, this is for the closed tube case, so none of this on the left is real, but this is a good way to think about what happens to the reflecting expansion fan. As I said, region 4 no longer exists, and this is now region 6, with P6 less than P3. Now consider an expansion fan hitting an open-ended shock tube. In this case, P4 is also the back pressure outside of the tube, since this is all open. For example, this could be atmospheric pressure in air if this shock tube has air as its left-hand side, gas, and it's open to the ambient air. This is not as common since we usually have a closed wall here and we pump up the left-hand side of the shock tube. In order for this to happen, you would have to apply a vacuum on the right-hand side of the shock tube so that pressure P4 is greater than the pressure we had called P1 before the shock tube diaphragm was broken. I have not seen this case analyzed in any textbook, though someone may have done it without me being aware. Now consider what happens at some later time T2, when the expansion fan has moved to the exit. Again, the control surface has moved slightly to the right. Region 4 is now gone, as previously, and these sound waves will start to bend around as they're exposed to the ambient pressure. Since pressure rises from right to left across the expansion fan, the pressure at this exit plane gets smaller as the expansion fan passes through. In other words, there's some suction at this inlet, so air starts to get sucked in to the inlet. Meanwhile, this pressure is still P3, and the gas is moving at speed V3, as previously. But this whole process is extremely complicated and depends very much on the geometry of this exit plane. If it's a sharp exit like this, you will get some flow separation and turbulence, etc. Now consider instead a nicely rounded inlet, which allows for a much smoother intake of the ambient gas without flow separation. In that case, at some later time T3, the contact surface has moved even farther to the right, and these waves have exited the shock tube. They eventually form spherical sound waves that travel out into the ambient gas. Meanwhile, we have a compression fan that moves to the right. Just as the pressure decreases from the leading to the trailing wave of the expansion fan, the pressure increases from the leading to the trailing wave of the compression fan. I'll call this pressure here P inlet, and P inlet is thus greater than P3. But in order for this gas to be sucked in, P inlet must be less than the ambient pressure P4. Again, the details here are very complicated, and it would be best to use CFD to calculate this pressure and the nature of this compression fan.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3.